I came across these the other day while I was searching more about VQE, and sort of, it's funny that it's kind of the tutorial for the Circ documentation. Circ is sort of a quantum computing library for Python that is developed by Google. It's open source as well. And I don't know, I thought maybe I should go through this because it's kind of like, even though it's not the VQE directly, but I kind of realized that it's the same thing. I mean, a version of quantum algorithms, I just quickly scan through these and you see prepare the ansatz state, make a measurement which samples from some terms in H, etc., etc. So, and at the same time, I'll learn a little of Circ. There's some code examples to go through here. So, yeah, so maybe that's something worth giving a try. First of all, I guess we'll need to install. I guess we'll need to install Circ. So let me see, and we'll install it in Linux and see how that goes. So let's see if that works. Doing something. There's some optional stuff for, I guess this is for PDF writing and plotting functionality. Maybe it will be useful. Let's give it a try. So, yes. And to check that it all works, I should type this in. Good. And I guess we'll try to use it sort of a Jupyter notebook or something like that to play with the code. Once this is done installing. Cool. I'll just pause this until it's done, and I'll come back in a second. You won't really realize in the video. I think. No, wait a second. I can't pause because I'm recording from outside the virtual machine. Whoopa. I think I've got. I think I installed Jupyter the other day. New tab. Does it? It seems like so. Start a Jupyter notebook. How do I do that? Okay, it's simply Jupyter notebook. So if I am, I'll just go to the projects folder. I have a couple of stuff in here, so I'll create another one called Circ VQE, and I'll just go there. Circ VQE, and here I'll just say Jupyter notebook, and that should open a notebook. Cool. Okay. And I guess I gotta create new Python 3 notebook. Okay. Never used that before from scratch, so we'll see how that works. See if the other stuff is done. Seems it's done. Now let's check that it's installed by doing this. It's thinking. Yeah, seems like it printed it. Cool. Perfect. So we're done installing it. So let's go back to the tutorial. Let's go through this first a little bit. I kind of realized I'm not recording on full screen, so that probably is better. Yeah, so you're gonna see more. You're gonna see more of that. Good. So, give me a second. So I go out of here. No, better. Yeah. So the variational. Let's just go through the background a bit. The variational quantum method in quantum theory is a. I'm recording. I hope I'm recording right, because I'm supposed to be recording here. Yeah, it's recording the desktop, so should be fine. Okay. Will be a pity otherwise. For finding the variational method in quantum theory is a classical method for finding low energy states for quantum systems. The Roth idea is that one defines a trial wave function, sometimes called an ansatz, as a function of some parameters, and then one finds the value of the parameters that minimize the expectation value of the energy with respect to these parameters. So that's kind of basically what I've more or less what I've been reading before about VQE, right? I mean, but that's a classical version. So it defines a trial wave function which is parametrized, and then one finds the values of these parameters that minimize the expectation value of the energy with respect to these parameters. This minimized ansatz is then an approximation to the lowest energy eigenstate, and the expectation value serves as an upper bound on the energy of the ground state. And that's kind of, and that upper bound, it's supposed to be useful somehow. So it's been realized that quantum computers can mimic the classical technique, and that a quantum computer does so with certain advantages, in particular when one applies the classical variational method to a system of n qubits. An exponential number in n of complex numbers are necessary to generically represent the wave function of the system. However, with a quantum computer, one can directly produce the state using a parametrized quantum circuit, and then by repeated measurements estimate the expectation value of the energy. The idea has led to a class of algorithms known as variational quantum algorithms. Indeed, this approach is not just limited to finding low-energy eigenstates, but minimizing any objective function that can be expressed as quantum observable. It is an open question to identify under what conditions these quantum variational algorithms will succeed. So the whole thing with VQE and I guess QAOA, it's just the same thing, right? It's you define a state, and then which is parameterized, and you measure it, and then you do some kind of classical minimization or optimization, and then you change the parameters, and that's it basically. And the classical problem will focus on okay. The classical problem we will focus on is the 2D plus-minus Ising model with transverse field Ising, whatever. This problem is NP complete, so it is highly unlikely that quantum computers will be able to efficiently solve it across all instances. Yet the type of problem is illustrative of the general class of problems that Circ is designed to tackle. Consider the following energy function. Okay. Where each S and J, Si and J, S sub I and J sub I sub J, and H sub I are either +1 or -1. Here, each index is associated with a bit on a square lattice, and the IJ notation means sums over neighboring bits on this lattice. The problem we'd like to solve is given this, find an assignment of S that minimize E. Yeah, so those are the kind of parameters. How does a variational quantum algorithm work for this? One approach is to consider n qubits and associate them with each of the bits in the classical problem. This maps the classical problem into the quantum problem of minimizing the expectation value of the observable. Then one defines a set of parameterized quantum circuits. Quantum circuit where the gates or more general quantum operations are parameterized by some value. This produces an ansatz state where pi are the parameters that produce the state. Here we assume a pure state, but mixed states are of course possible. The variational algorithm then works by noting that one can obtain the value of the objective function for a given ansatz state. The variational algorithm then works by noting that one can obtain the value of the objective function for a given ansatz state by preparing the ansatz state, making a measurement which samples from some terms in H go to 1. So this is repeated measurement, and note that one cannot always measure H directly without the use of quantum phase estimation. And this is, I have to thank, how is he called? I'm really bad at names. Really bad at names. I'll just, I don't know if I can find that in my bookmarks, probably, maybe. Or in my retweets and replies, probably. Yeah, Guillaume Verdon. I don't know if I'm pronouncing your name correctly, but thank you for the answer. That was super insightful. So phase estimation measures the energy value and stores it on an additional quantum registers in a binary representation. VQE uses quantum. So the thing is, I kind of forgot because I basically learned about phase estimation within the context of Shor's algorithm, and I was focused on the fact that what it does is it basically finds that that period of that modular operation. I don't know if I'm using the right words, but anyway, I kind of forgot the fact that because I read in the O'Reilly's book that really what phase estimation does is it gives you the eigen phase of a quantum gate of an operation, right? If you do that phase estimation using a given eigenstate of that operation. And if you don't know what I'm talking about, go check the book. I definitely recommend that. And that's exactly the one that corresponds. That eigenphase is what corresponds to the to that energy level that we're looking for. Because I think the whole thing here is about the properties of the Hamiltonian, which is basically in a matrix form has that property that its eigenvalue basically represents that kind of that energy value. And I think that's basically that's the point. What did I write? I write because the operation is Hamiltonian. Its minimum eigenvalue is the minimum energy. Kind of sense. Yeah, I mean that's what I suspect. So so one relies on the linearity of expectation values to measure parts of H in step 2. So one relies on the linearity of expectation values to measure. One always needs to repeat the measurement to obtain an estimate of the expectation value. How many measurements needed to achieve a given accuracy is beyond the scope of this tutorial, but Circ can help investigate this question. Because the idea is you don't want to use phase estimation because it's prohibitive in terms of it requires you to double up or to add more qubits into your system so that you can encode, so that you can keep that or get that outcome. Whereas what phase estimation is using is quantum expectation estimation. Is this a real term? Quantum expectation estimation, or is it that? Oh, wait a second. In quantum mechanics, the expectation value is the probabilistic expected value of the result measurement of an experiment. It can be thought of as an average of all the possible outcomes of measurement as weighted by their likelihood, and as such, it is not the most probable. It is not the most probable value of a measurement. Indeed, the expectation value may have zero probability of occurring. Ah, so it's the okay. So it's the average of all possible outcomes weighted by the likelihood. Um, Measurements which can only yield integer values may have a non-integer mean. It is a fundamental concept in all areas of quantum physics. But how do we know that? How can? How do we know that that equals the answer that you would get with the phase estimation? That's what's not clear yet to me. Mm, 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 mm. Okay, but that's still to solve. So, because phase estimation tells you something about that, it tells you that property about your Hamiltonian or about the matrix. Uh, but how would then repeated measurements and averaging through those repeated measurements give you the same outcome? That's what it doesn't seem so obvious. So obvious to me. Okay, so no. The quantum computer to obtain estimates of the objective function for the ansatz. This can then be used in an outer loop to obtain parameters for the lowest value. Yeah, for this for these values, one can then use the best ansatz to produce samples of solutions to the problem, which obtain a hopefully good approximation for the lowest possible value of the wave function. Yeah, but that's then best ansatz to produce samples of solutions to the problem, which obtain a hopefully good approximation of the lowest possible value. So the quality of that also, it all depends on the ansatz you're using. Create a circuit on a grid. Okay, so let's get into it. Or you know what? I think I'll stop here for this video. I'll just make another one where I go ahead with the actual stuff. I got it installed and I went through the background, but this is still not clear to me. So how come that the is there anything here about the face? No. Because it all kind of clicked together a little bit, right? Because basically, if you open Quirk, I can quickly show that it kind of all clicked together with also what Craig was mentioning when I asked about what the hidden phase is that now has been renamed to global phase. And he's like, yeah, that's useful when you want to take advantage of the phase kickback. And I think that I understand now that, for example, if you've got a Hadamard here and you've got a 1 here, and you apply a control Z, right? So you're gonna have, if you just measure here, you have a phase of 180 degrees here, And that's because is it rotates 180 degrees? Hmm. After the Hadamard. Yeah. So, okay, because I thought, because the global, 90 degrees. Um, hmm. That's exactly the 90 degrees that you see in the rotation. The 180 degrees that you see here in the rotation. Uh, yeah. If I would add a, say, Hadamard incoherent, a T, then you've got 45 degrees. That's the phase here. Yeah, anyway, I don't know what I was trying to explain actually. I mean, what I don't quite get yet is that the expectation value is supposed to, why is it supposed to be phase dimension measures the energy value and stores it on an additional quantum registers in a binary representation. VQE is quantum expectation estimation, which uses more runs to estimate energy to the same precision but doesn't need extra qubits. But if you would measure the uh, man. So A measured in a state, this is the expectation value A in a state that is denoted as mathematically A is self-adjoint operator on a Hilbert space. In the most commonly used case in quantum mechanics, is pure state described by a normalized vector in a Hilbert space. By the observable, the expectation value of A in the state phi is defined as this. If that is considered, if dynamics is considered, either the vector phi or the operator A is taken with independent. If A has complete set of, if A has a complete set of eigenvectors with eigenvalues A sub j, then one can be expressed as so so basically it's the sum of all the eigenvalues times the eigenvectors. Okay, so this is just the, okay, so this is then sort of the it's more the mathematical level, that this is the way, because it's a matrix, and this is probably part of the definition of eigenvalues and eigenvectors, which I'm not super familiar with. And so measuring the state many times and doing the average will actually give you a similar approximation. That's pretty bizarre though. I I mean, that's something that you can't figure out unless you really know the maths behind the way matrices operate. But it's still, for me, it's this is where I'm scratching the border for me, and I should probably catch up with some of the maths behind this. But so this is basically, if you measure measuring the circuit, because essentially you have transformed, because you've essentially have transformed the state by applying the matrix. And this is exactly the eigenvalues and the eigenvectors. I mean, eigenvectors and eigenvalues. In linear algebra, eigenvector and vector is a non-zero vector that changes at most by a scalar factor when the linear transformation is applied to it. There's a direct correspondence between n by n square matrices and there's a direct correspondence between n by n square matrices and linear transformations from an n-dimensional vector space into itself. For this reason, in a finite dimension, it's equivalent to define eigenvalues and eigenvectors using either the language of matrices or the language of linear transformations. Geometrically, an eigenvector corresponding to a real non-zero eigenvalue points in a direction in which it is stretched by the transformation, and the eigenvalues is the factor by which it is stretched. So basically, the eigenvectors and the eigenvalues are really what what define the matrix and what define the transformation. So okay, so by measuring by measuring the state many times, you actually end up measuring the result of the transformation. And so I guess, and that's the energy. And I guess the trick here is, the thing with the phase estimation is not that it gives you that energy, is that it gives you the eigen it gives you the eigenstate, it gives you the eigenphase or the eigenvalue, so that you can calculate the energy using that. Okay, I think that is the way. I think that is okay. Now I kind of I think this is it. This must be it. Cool. So I'll leave it here for now. Okay, I'm actually happy that I figured that out. I mean, I hope that I figured it out well. So basically, I'm just trying to repeat this. So, it's nice. I wanna. I feel I should really dive into eigenvectors and eigenvalues a bit more. I feel I just really scratched the surface, but it seems this is really sort of the way that the matrix. This is the things the matrices are made of, or the thing that describes the matrices, and so. And therefore the transformation. So when you apply the transformation to a state, and that's what you do with a circuit in this case, you're basically when you measure that, you're measuring the result of the transformation. So with the phase estimation, you would be able to just in one run get the for a given eigenstate, you would get a the eigenphase, because that's what the phase estimation gives you. And with this, you would be able to then, outside of the quantum circuit, calculate the energy. So calculate the objective function to minimize. So you would do this with a run. But the idea here is, but you need more qubits, because that's what the phase estimation needs. And so by just doing the expectation value estimation, basically you already get the result at the end, because you're just measuring many times and then averaging through that. Okay, cool. Perfect. We'll just get out of this, and basically, oh yeah, that's pretty cool stuff. I'm definitely looking forward to this course and exploring this stuff in here, to the course in here, understanding quantum computers. that's definitely an interesting idea. Cool.